I love this course. Let me take you first back to 1905. So, 1905 was the start of the quantum in many ways. Yet, much of your quantum education has nothing to do with that. In the photoelectric effect, so the field acts like a particle. And it also gets annihilated. So it disappears. So, when you do quantum mechanics, normally all your stuff is, wave function psi star psi, and particles always stay there. This idea of having a quanta disappear out of existence is something that is unusual. And the idea that fields behave like particles. The converse is that particles also behave like fields. So you take an electron, you shine it through diffraction grating, and you get, these typical diffraction peaks out of electrons. So, but nevertheless, the quantum mechanics that you've seen so far has this disparity between the electrons and the photons. And so when you first do the photoelectric effect, it's sort of funny. But even these particles also get created and annihilated. So you could do, for example, there are reactions, E plus E minus goes to mu plus mu minus. Now particles, a positron and its antiparticle annihilate and appear as different types of particles. Again, things that you can't describe in your usual quantum treatment. So quantum field theory solves this. So QFT, quantum field theory, is the completion of quantum mechanics. It puts everything on the common footing. So the way we treat fields like the photon and the way we treat electrons is going to be unified. They're all going to be treated exactly the same way. You can describe all these processes that you couldn't describe otherwise. Quantum transitions go on. And at the same time, you build up a whole set of powerful techniques that are much more convenient to use in real settings than are many of your standard techniques. Now, historically, much of this happened because of relativity. It's because of relativity that you can have some of these things like E plus E minus annihilating, there's particles and antiparticles wasn't appreciated. But the field theory technique is completely independent of that. We will do a lot of relativistic stuff in here, but that's not the heart of the matter. The heart of the matter is this idea of quantizing fields, which we will do today. So there's our framework. Let's do a little bit of bookkeeping. So the course. I handed out the syllabus there. The syllabus is the way I taught it the last time. I will probably change it around a little bit. As always, one adjusts this thing, but it gives you a sense of where we hope to go in it. It's a basics course. It's not too fancy. If we want a fancy course, we have to go beyond this, because this is sort of the transition, the prelude to all the wonders of quantum field theory. The other thing is that I'd like to teach it for all disciplines. So actually, can you give me a sense here of how many people are interested in condensed matter dominantly? So there's condensed matter, and particle, nuclear dominantly, okay, and people who don't know dominantly. Okay, I have a sense. The last time I did it, I had expected I was going to do more condensed matter than I ended up actually accomplishing. Maybe I'll try to make up for that a little bit this time, if we can. However, I do use relativistic notation a lot, because it simplifies things, and actually you can see the essential. Again, the relativity isn't the essential part, but having the notation be simple allows that to jump out at you. Okay, and there are some things that I need to do that are special for the particle nuclear types, but I'll try to enhance the condensed matter a bit. Okay, the books, I sent many of you an email in advance in case you wanted to get it in advance. One of the standard references for the particle nuclear crowd is this book by Peskin and Schroeder, and if you can get it for $4.99, you're welcome to try, which it doesn't sell for that normally. I've been trying to find a good textbook for the condensed matter types. This book by Atlin and Simons matches our start well, and then both these books have way more than we can cover in this course. It's just not going to be possible to cover anywhere near the content of either of these books. So that's, but they all carry much of the same material at the start. So those are your options there. I should say that for the condensed matter folks, there's also effectively a whole good textbook online by a professor at the University of Illinois. If you're interested in getting that link, you can come see me and I'll give you that link. I have to admit I printed the whole thing out because I think it's a nice book. The homework plan. Okay, there's a different philosophy in this course than in many of the introductory courses. So those of you that had me before in E&M, there's a sort of a muscle building course where you're trying to develop your skills at analysis. Here, I'm expecting that many of you are involved in research or do have other things going on, such that I'm not intending to give you the same level of homework, the same quantity of homework. But you need to do some work in order to do the to understand how to do it. These things are all done by calculations, and you just have to do that. So it'll be more of the level of exercises. So there'll be weekly homeworks. That's the entire content of your grade. Again, grades at this level are not the crucial thing. It's understanding it. So the homework is aimed at understanding. I'm happy to mentor anybody in my office as much as you need. This is a course I enjoy very much. I'm happy to have you come by and talk about it. All that is geared for you to understand. Okay, and hopefully not to swamp you too much, but okay. For those of you who haven't seen this little setup here, I also do teach on this. I post the notes on the web page. It's actually the whole recording is there, so you can go back and review it if you want. You may or may not use it, but in the past people have used it enough. Office hours or anytime you find me, which should be relatively frequent. So all of them are office hours. And if you want, on my web page, I have a link to Google Calendar. You can check my schedule for known conflicts. Hopefully it's okay. Okay. This, I should say, also for the people that are new to this recording thing, it's not an excuse to skip class. This particular type of class is one where we really need to have everyone here to talk about things as we go through it. Again, it's a mentoring situation as much as anything. So we want to have talk and questions and all that stuff in class. Anything I should have said? Nobody? No? If not, let's... Yeah.
Will we have to buy a special...
You don't have to. So, if you're interested, you may just borrow somebody's book from somebody who's taken this course or as an advanced student, if you're going to do field theory in the future, you'll need a reference book. And the reference books probably determine, on what type of field you're interested in, and it's hard to predict. I have, in my office, I have something like 25 field theory books, some enormous number, okay? You're welcome to browse them if you want to take a look at one of them on some section where it is. I don't, all books cover the same material at some level. They all do it slightly differently. I don't follow any particular book, so, but you'll find the material in something. So if you're going to continue to do field theory type things, you'll want a reference, but other than that, you don't need it for the course. Okay, you'll have all these notes and you'll have the ability to walk in and ask me any question you want. Okay? Anybody else? All right, so our first task is to construct a field. We're going to construct it, and then after that, we're going to quantize it. And so by the end of today, we should have a quantum field for you. Okay? I'm going to start with the standard definition of a continuum mechanics system, of a field. A field is a continuous function that satisfies a wave equation for us. So I'll call it phi of x and t. It's going to be a function of space and time. And technically, the mathematicians, would say that any function of space and time is a field. For us, it also has to satisfy a wave equation, which this one will be the usual one. So let's start off with this typical example. We're going to take mass points separated by springs. Okay, so there's a bunch of masses there. Their spacing is going to be a. They're going to vibrate up and down, so their position is going to be y. That's going to be a function of time. And they'll each have mass m. There'll be a uniform mass on a string. Okay? So we start off with our variables being yj of t. And the Lagrangian is the sum over j 1/2 m y dot squared. And if we had a general potential, you'd have the general potential, but we're going to then, of course, Taylor expand it around the minimum, as you'd always do for this. 1/2 k yj minus y, let's make it plus 1 minus yj squared. It's a Lagrangian that's a function of the coordinates and the time derivatives. And the action is the integral dt of this Lagrange density. Okay, so classically, we define the momentum is the derivative of the Lagrangian with respect to y. It's yj dot. There's the dot, which in this case is just m yj dot. The Hamiltonian is sum over j pj yj dot minus the Lagrangian. And we are always instructed to write this as a function of the momentum and the coordinates. Okay, and if you do that, that turns into sum over j pj squared over 2m plus 1/2 k yj plus 1 minus yj squared. Okay. So there's our setup. If we look at this, I want to write this as a continuum system, so we'll go to the continuum. When we take the continuum here, what we're really doing is going to long distances. So, you know, it's actually more logical to think of keeping the spacing fixed, but looking at over very, very many units of this, such that the solutions that you're going to see on this are wave-like solutions, even though at small scale, say, there are these mass points. Okay? So to take the continuum, we're going to do this carefully because it ends up giving us the precise normalization later on when we quantize. So x is going to be a times j. So this is just how far down this thing you are. X, we've got all these guys going down here. We're at the jth one, they're each spaced a apart. X is a times j. The summation over j with a factor of a there turns into the integral dx. Okay, so the little dx is a, and you sum over all of them, so that's just the definition of our integral. And the big one, though, the one that you have to play with a bit to make sure you get it right, is yj of x is going to be, well, it'll be replaced by phi of x, so j becomes, I'm sorry, back up. That should not have been x, that's a t, of course. Yj of t, the time dependence of a particular point on that. The space dependence of that becomes x, the time dependence stays t, and the right normalization turns into 1 over the square root of ka. K being that spring constant. Okay? If you do that, let's pick one of the pieces, and the second one I won't do the algebra on, but if we have sum over j 1/2 k, leave a space, yj plus 1 minus yj squared. So that's one of the terms in there, that's the potential term. I'll divide this by a and write a squared there. Okay, well, you can recognize the derivative there, the yj plus 1 minus yj divided by a for small a is just the spatial derivative. That's that definition. So this becomes collecting terms. I have sum over j a. I put 1 over a here, 1/2 k a squared. So I've just written that way. Then, using my definition of phi, it becomes 1 over k a times d phi dx squared. And you see the k's cancel. The first sum times a becomes the integral dx, and we get exactly integral dx 1/2 d phi dx squared. Okay. The other one is pretty similar. I won't do it. Sum over j 1/2 m yj squared. Well, you can see that it's going to be turned into the integral dx when I do it out. It'll be phi d dt. That says dt squared. And whatever's left over, it gets collected up into a constant. Just 1 over v squared. Okay, Rich. Yeah, they do. This guy goes into the integral dx. Okay. Then these guys cancel there. Everything but that one canceled. Yeah, that's right. Okay? Good. Thanks. As I say, it's worth paying attention to some of these things as we go through it, just because it's the normalization actually turns out to be important. Okay. So in the second one, everything that doesn't turn into d phi dt gets collected into 1 over v squared, and we get v is the square root of k a squared over m. Okay, there's, okay. So then the action is the integral dt dx 1/2 1 over v squared d phi dt squared minus 1/2 d phi dx squared. Okay. It has this general form, the integral dt dx of a Lagrange density. Okay. Lagrange density because it's the Lagrangian is itself the integral dx of the density. That's a function of the field and its time derivative. It's also a space derivative. I can put that in there too if you want. Okay, so in general that will be the case. And with a Lagrange density, the Lagrangian is the integral dx of the Lagrange density. Okay. Any questions about that? So here's our Lagrangian. This is again, this presumably is up to notational issues, the same thing that you've seen in classical mechanics. So let's just go through it. Yes, big one. There is a 1 over 2. Thank you. Very good. There's a 1 over 2 missing there because I want it down here. That's actually a convention, of course, because this there is a conventional normalization which we will not explore today, but we'll come back to. Okay. Anything else? All right, let's get the Euler-Lagrange equations. Okay, so to do the variational principle, we'll imagine that this field phi of x and t has some value, phi bar of x and t, that satisfies the classical equations of motion, satisfies the equations of motion, plus delta phi. So this guy's the classical solution. And typically one sets delta phi of x and t equals to 0 on any boundaries. Or at infinity. Okay. This is in space and in time. So if you we will start treating space and time much more together. We already have up here the dt dx, but any endpoint, anywhere you have to evaluate this at infinity, you just set it equal to 0. Okay. Okay. Then you look at the variation in the action. We're going to set that equals to 0 by the principle of least action. So that's going to be set equal to 0. And if you just plug through this, it's pretty easy to do. It's the dt dx. And we have to expand what's sitting up there, phi bar and delta phi. Okay, well these are quadratic, so it's pretty easy to expand that. The first term, the term that's the variation, has 1 phi bar and 1 delta phi. Right? So there's the action has one with both being phi bars, one being the classical solution 1 delta phi, and 2 delta phi's, which you drop because it's small. Okay? Remember the logic. So the first term is 1 over v squared d phi bar dt d delta phi dt. Right? So if we'd expanded that, there's the cross term carries the factor of 2, cancels the factor of 2. Okay. And the second one is minus d phi bar dx d delta phi dx. Everybody see that there? I don't know if I'm going too fast, too slow. Okay, so that's the first variation of this, which is going to have to be equal to 0. The standard trick at this stage is you integrate by parts. Integrating by parts takes this time derivative, flips it over on that on the other quantity. The surface term is 0 by this assumption here. It's either at infinity and you set everything to 0, or on the boundaries, the time boundary or the spatial boundaries. Doesn't matter. Likewise, this one you flip over, it becomes on the other side also. So after you integrate by parts, this turns into integral dt dx minus 1 over v squared, second derivative phi bar t squared plus second derivative with respect to x phi bar, all multiplied by delta phi. Okay. And the usual argument then is that if this is true for any possible delta phi of x and t, then the quantity in square brackets has to vanish identically at every single point in x and t. And so we end up with the wave equation, 1 over v squared d by dt squared minus d by dx squared on phi bar x and t equals 0. So that's the wave equation. Okay. Okay. So that's all to lull you into sleep there, because you're also familiar with the derivation of the wave equation this way. Now, next step isn't quite as obvious. We're going to do the Hamiltonian. And normally when we're doing point mechanics, we have the Hamiltonian, the momentum is the partial of the Lagrangian with respect to y j dot. Okay. Now, yj has become phi of x. So it's clear that the corresponding guy is going to be the derivative of the Lagrangian with respect to phi dot of x and t. So let me try writing that a little clearer. Okay, so that's a dot, that's a time derivative. And so that's going to play the same role. That is going to be defined as pi of x and t. It's also a field. And one of the things that is going to start being a little bit less trivial now is that in simple systems, this guy was really the momentum that you plugged into F equals ma. You know, it's the momentum that when things hit each other, you feel that momentum. This is going to be a little different beast. It's also a field. It's not going to be the momentum carried by this wave. In the end, we're going to quantize it. We will find the energy in the wave. We will find the momentum in the wave. The momentum is not going to be that. This is so, but we'll still call it the canonical momentum because it plays that same role. There's probably some analogy I could work up more, but it's best to just disconnect it from the usual momentum. Okay. So in this case, if we take that, it's 1 over v squared d phi dt. Okay, so now we have a second player in the game, which is the canonical momentum. Okay, we can do the Hamiltonian in a couple ways. The Hamiltonian was sum over j, pj squared over 2m plus 1/2 k yj plus 1 minus yj. If we just go through the same set of steps, you can sort of see the answer. Let me just write it out for you. It becomes the integral dx of, well, the obvious one is the second one. That's the 1/2 d phi dx squared, because that's unchanged. Okay, so you just change the minus sign, right? When you do take pi, well, when you take the Hamiltonian, it's p y dot minus l, and so you get the sign change. And the second one turns into also the same thing. It's 1 over 2v squared d phi dx dt. Sorry, dt squared. Okay, which, technically we should write this as 1/2 pi squared v squared. Okay. Phi dot is pi v squared, so 1/2 over 2v squared. Phi dot squared is pi squared times v squared. Okay. So that's one way we could have done it. Or we can do it the field theory way, the classical field theory way. We will take the Hamiltonian as the integral dx Hamiltonian density, just like a Lagrange density. So here's the Hamiltonian density. And the Hamiltonian density is defined as pi phi dot minus the Lagrange density. Okay. That's a definition. It turns out to give you the same result. That also equals 1/2 pi squared v squared plus 1/2 d phi dx squared. It's, again, formally a function of the field and the canonical momentum. Okay, one thing I need to do, let's see, I want to do a little bit of something on normalization here. The second line looks like it's a bit of an analogy. It's actually, you would derive it the same way. You go through the same steps showing that this is a conserved quantity. I'm going to postpone that stuff till we do Noether's theorem, and we can do a more general case of this for any field theory. But right now, that's what the answer is. Questions about it? Okay, here's what I want to do on the normalization. We had Pj was my dot j, and remember we converted that over to a continuum notation, so we're going to put that in terms of phi dot of x and t. The normalization was 1 over the square root of Ka, if you remember, and there's this m floating still there. Okay. Now, if I use, at this stage, 1 over v squared is m over k a squared. That was my velocity, if I remember correctly. This is 1 over v squared a square root of ka phi dot, and it's a square root of ka pi. Okay, and if you go back and you plug it through the equations that are up there on the Hamiltonian, you see this works out. Okay, I want that for my next step. So we have the coordinate yj of t is 1 over the square root of ka phi of x and t. And pi has that feature there. So that's where the explicit stuff goes. Okay. So that's the classical mechanics. Got you ready for the quantum mechanics now?
Is it all just for that example, or is it the general result?
So this is just this example. So that step is only true for this example, because what I'm doing is I'm going from mass points. What we're going to do is we're going to get a commutation rule between phi and pi that mirrors what we had between coordinates and momentum in quantum mechanics. And that we're then going to generalize to any wave equation. Basically, the logic will be, I could have just started out with my Lagrangian, my action principle, without knowing the underlying physics there. So after today, except when we're doing analogies, we're just going to start with a Lagrangian that has a field in it. We're going to find the canonical momentum. We're going to quantize it and go on. But what I'm doing right now is I'm building up to the derivation of what the quantization rule should be, okay? Because we don't know that yet. And then we look at the consequences turn out to be actually pretty astounding. You get quanta, just like photons, out of this system. Okay, ready for quantization? Let's go. Okay, so normally what we know we would have done is we would have taken yj, pj prime, so the coordinates are 2 different points, If they're the same point, they satisfy the commutation rules. If they're distinct, they give 0, right? That's how you would have quantized that system. Okay. So let's do that. We then write this as 1 over the square root of Ka phi of x and t, and p, by the calculation we just did, is square root of Ka times a of pi of x prime and t. Okay. So there's a commutation rule now. And we see that the square root of Ka's cancel, so that Ka business doesn't play any role. There is an a left over, and so let's just write it out here. It's phi of x and t commuted with pi of x prime and t is IH bar delta j prime over a. Okay, but we're now at the stage of having this funny. We're not quite there yet. You can tell we've got a Kronecker delta left over, which we need to make a continuum limit on that, and a 1 over a. Now, you can sort of see the delta. This is going to come out as a Dirac delta function, as the continuum generalization of that. So let's just talk it through first. For small a, let's imagine taking a goes to 0 now. If j is equal to j prime, this goes to infinity. If j is not equal to j prime at 0, so that sort of looks like it might be a good Kronecker delta function. And it is. I'm going to then, let's just write it here so we have it. It's IH bar delta of x minus x prime. That's the continuum generalization of that. Now let me just do the correspondence.
Why do we use the same time?
Yeah, it's a great question. Great. There's a good deal of physics in that. And I'm not going to explain it completely right now. But I will, well, I'll tell you the answer, but I won't go through the elaborate demonstration of it. It turns out what we're actually doing here is we're actually doing the Heisenberg picture, where the coordinates, normally you take x and p to be time independent. That's the Schrodinger picture, and your states evolve. Here, x and p carry time dependence. That's what we've done is we've transformed to the Schrodinger picture, to the Heisenberg picture, where they carry the time dependence and the states are static. I will do that as a separate unit later on. But you actually picked up on one of the key points here on this commutation rule, so let's write it out here, is that this is an equal time commutation rule. These things are defined at equal time. Okay, very good. That's okay. So it's my hint about Heisenberg and Schrodinger is designed to let you relax, and we'll come back to that. Okay, right now I want to focus on this delta function, so the correspondence. Okay, we know that the sum over j of delta j prime is equal to 1, right? Let's make sum over j primes, actually. Let's make sum over j prime. Okay, it's 1 whenever j is equal to j prime, and it's 0 everywhere else. So it sort of looks like a delta function. If I write this as the sum over j prime a delta j prime over a, we already saw that this first guy in the continuum limit has the correspondence as integral dx. And so the second guy then had better have the correspondence x minus x prime, because in this case it's x prime, sorry, j primes integral x prime. That's something that we want to be equal to 1. So in case you ever need it, the continuum limit delta x minus x prime is the limit a going to 0 of delta j prime over a when x is equal to ja. Okay, so that's the correspondence there. Okay, but the big thing is we've now identified the rule for quantizing the system. Whereas before we had rules on y and p, coordinates and momentum, here it's on the field and it's canonical momentum. Okay, so there's a big step. We're actually making enormous progress. Anyone want to ask about that? Anything else about that? All right. Next step is to actually carry this out, to force that solution, and the end of the game comes out the idea of quanta. Okay, we get energy as h bar omega for each of the quanta, and they come in discrete bunches. Okay. All right, so I'm going to do this. So here's quanta coming out. I'm going to do this first in discrete notation. Okay, discrete notation here means that instead of having integrals in over the energies, we have sums over energies. So there's going to be a discrete set of things. So you might want to do, for example, box normalization. You put this thing in a very big box. So here's our waves going along. The box length is going to be L, and you impose some boundary conditions. The boundary conditions are not that important, but the easy one to think about is just assuming that the field vanishes at the endpoints, and then you just get, n pi over L as your energies. But the main thing is that the energy levels are discrete. Okay, this makes the math a little easier for us. It's also a good physical situation for many things. Then we'll come back and we'll do the continuum notation maybe even next time, soon. Okay? So we want to solve the solutions. Okay? Well, it's sines and cosines, so we have 1 over v squared d squared dt squared minus d dx squared phi of x and t. Those are going to be our fields. That's equal to 0. So we know that the fields, up to some normalization, they go like e to the minus I omega. Let's put an index on the t. Omega, actually I'm going to use the index s. Sorry, st minus ksx plus the complex conjugate a real field. This is a real field. So it's, you know, you take sines or cosines of that, and omegas and k's get quantized or discrete. We have omega squared over v squared minus k squared equals 0. So omega s is ksv, and all we care about is that that's some discrete label. Okay. So our most general solution is we take phi of x and t, sum over this f, there's some normalization, e to the minus I omega s t minus k s x a of s plus the complex conjugate is e to the plus I omega s t minus k s x, and I will use this as a dagger because I'm now going to start treating this as an operator because this is suddenly going to be quantum. Okay, we're going to have to, we know already that we have to make these things into not just classical numbers because we have that quantization rule to satisfy up there. So they have to become now operators. You know, they not everything can commute because if I take pi from this and try commuting it with phi, if these are just plain old numbers, everything cancels, everything commutes. So they have to be operators that aren't going to commute. Okay, so we're on our way. So the conditions are, okay, I'll give you the answer and then we'll show it. We're going to take a of s with a of s prime. So two creation operators, well, okay, two a's, they commute. We're going to take a of s with a dagger of s prime and say that's delta f s prime, Kronecker delta. And in satisfying the quantization condition, so there is a normalization choice here. I'm going to take n of s is the square root of, well, it's h bar v squared over 2 omega s L. Okay. If we choose that, we will have a nice quantum field. Okay. So in this case, pi, okay, remember it's 1 over v squared d phi dt. Well, it's the sum. Let me make it the sum over s prime just because I know my next equation I have to put s's and s primes in it. I've got n of s prime. When I take that derivative, there's my solution sitting there. I bring down a minus I omega. So let's do minus I omega f over v squared. I then get my exponential back again. And on the second term, because I pulled out a minus I, it's really a plus I in the second term when I take the time derivative. So I have an extra minus sign that sits there. So let's put a star there so you don't miss it. E to the plus I and a dagger of S. And I said I was going to do S primes everywhere, and I didn't do it. So let's put primes on everything. Prime, 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 prime. There. Yeah, I got all my primes back in, I think. Good. I think that's... Okay. Anybody? All right. So now comes the demonstration that we're going to check that this satisfies the commutation rules. So phi of x and t with pi of x prime, same time. All right, so let's see. If I can get them both up there. Yeah. So it's the sum over s and s prime, ns and s prime. There's a minus I omega s prime over v squared sitting out in front there. And then I have a commutator. And so let's be a little bit sloppy because we'll be able to see where things come in a minute. It's e to the minus I stuff a of s plus e to the plus I stuff a dagger of s commuted with e to the minus I stuff prime a of s prime minus a dagger of s prime e to the plus I stuff prime commuted. Okay. So there's four terms here, two of which are interesting for us. The a with a disappears by our rule up here. A dagger with a dagger disappears by commission conjugating that rule. I have a with minus a dagger. So there's a minus sign that comes out. And then there's an a dagger with a, which is the same sort of thing, except I reverse the indices. Those are going to give me a delta SS prime. So let's see if I can skip a step of writing both those out there. So the delta SS prime means there's only a sum over S, ns squared, because S and S prime are the same, over omega S over V squared. But that becomes a plus. Okay, this minus sign here and that minus sign there make it a plus. And the other one, remember, was the reverse order a dagger a, so there's a minus sign also associated with that. So those two things give me a factor of 2. And then I get the stuff and stuff prime multiplying each other. Okay, so let's remember what stuff and stuff prime were. This was omega t minus k dot x. This is omega t minus k dot x prime. Omega and k are the same now because s and s prime are the same. So s and s prime are the same, meaning that omega is the same also. So, but still, we still have here x and x prime being different. So there is still something left over. Here's what's left over is e to the I ks x minus x prime. Okay. You now look up at the cleverly chosen normalization up there, and we note that this factor sits right there. So the 2 omega s cancels, the v squared cancels, it becomes I h bar over L. So this turns into I h bar sum over S 1 over L e to the I k x minus x prime k sub s. Okay. And this guy is a representation of a delta function. So all my E&M students will immediately jump up and down and say that when you have an eigenfunctions like you have here, sines and cosines, this is the Fourier sum representation of a delta function. If you put boundary conditions, it is just exactly the Fourier sum. So this is I h bar delta of x minus x prime, which is exactly what we wanted it to be. Okay, questions about that? So, you know, in a sense, we haven't solved an awful lot yet because we've just traded one commutation rules, phi and pi, for another set, A and A dagger. Okay. But those guys are starting to be familiar. And I'm actually clearly not going to be able to do the whole calculation here, but let me get you into the punchline that we'll pick up next time. Let me go to the Hamiltonian. Okay, the Hamiltonian is the integral dx, 1/2, 1 over v squared d phi dt squared plus d phi dx squared. Okay, it's positive definite. And what I'm going to do, I'm going to do it at least in some detail because there actually is a couple things that are relevant in there, in the calculation. Some of it's just a long, brutal calculation, which is a bit painful, but we will go through it because some of it is actually important to see the details. But you do ... and a miracle occurs, and this turns into sum over S h bar omega S A dagger of S A of S plus 1/2. Okay, so basically what we've done is we turned this into a bunch of harmonic oscillators. Okay, we'll deal with some of the details here next time. But once we have a bunch of harmonic oscillators, we know what the answer is. This is the number operator. Our states, the energy of our states, dropping this is going to be 0-point energy, dropping E0. The energy of a state is going to be the number h bar omega, and so we will get our quanta out here. Quanta up here magically. And it's actually, I still find it, having done this many, many times, amazing that just by turning the crank, that the classical mechanics crank that we sent up before for Lagrangian mechanics gives you this Hamiltonian. You then impose that commutation rule, and you get exactly this harmonic oscillator condition. In principle, you could get all these off-diagonal pieces. You could get time dependence because these are functions of time. Time dependence disappears, off-diagonal terms disappear. It just comes out as exactly the number operator. And this miracle occurs over and over again in all the other field theories that we do. You know, when we do photons, we do spin-a-half particles. You do non-relativistic. It's actually more obvious. But you do all the other fields, the same miracle occurs. You just turn the crank, you get a Hamiltonian that's just the harmonic oscillators, and you have a very easy interpretation of the states with all these quanta. Okay? Yes? Right. Yeah. Yeah. Well, yes, okay, so it's a good point. It's, however, what we have done is, the way it's not so strange is, if you think back of doing some finite number of harmonic oscillators, the way you would actually solve this classically is you'd find the normal modes. You'd find the modes that have definite energy states. And these guys are the states with definite energy. These are the normal modes, which in the continuum limit turns into the waves. So if you're doing small normal modes, you know, you might have done, you know, things like this. There's one of the normal modes that oscillates at a different frequency. That's the discrete approximation of a wave, and the waves then become the normal modes. So it's actually more that it's not so much that the original interactions were harmonic oscillators as it is that the normal modes are decoupled harmonic oscillators. That's the reason it's not that much of a surprise. So we found the normal modes, we've quantized the normal modes. These A and A daggers are the coefficients of each normal mode, and that's our quantum. So this will be our procedure. We will, of course, develop it here. Okay, we'll see you next time.